Welcome, ladies and gentlemen, to a discussion about something called Coulombic attraction. Yes, the B is silent. This particular concept is going to be helpful to you as you complete your POGL. In particular, questions 3 and 5 ask you to use your knowledge of Coulombic attraction to explain the patterns you observe. So while I could have you do the entire POGL on Coulombic attraction, this discussion will shorten it up and hit the key points. I don't think we need to spend the time to do the entire activity. We're just going to go through some of the models that came from the POGL to give us a little bit of background. So here you see I have the Y. Coulombic attraction is the attraction between oppositely charged particles. So keep in mind that when you have an atom, there are protons in the nucleus that are positive, that are attracting the negative electrons in the electron cloud around the nucleus. That means that there is Coulombic attraction occurring between the nucleus and those electrons. We can measure or describe the force of attraction that occurs. So in some cases it can be more weak, and other times it can be more strong. So we're going to look at two variables that affect the strength of that attraction. The first one that we see here looks at distance and attractive force. So you'll see that for our 3 different distances that are measured, as we go from A to B to C, we are increasing the distance between the charged particles. As we increase the distance, when we look at the force of attraction and the values are measured in newtons, you will notice that the force of attraction decreases. So if you think of this like magnets, if I would hold 2 magnets relatively close together, it's pretty likely that one magnet will attract to the other. If, however, I would hold the magnets much further apart, it is much more likely that when I let go of a magnet, it would simply fall to the floor. The force of attraction between the 2 magnets of equal size really aren't going to be as strong if they are further apart. The protons and the electrons on the outside of the atom work in a very similar way. The farther away those valence electrons are, the weaker the hold of the nucleus on those electrons. So let's look at this in the context of some real elements. Here you see the alkali metals. This would be our first column on the periodic table, our group 1 metals. And we've pulled the first 3 energy levels except for hydrogen. So we're looking at row 2, row 3, and row 4. You can see that reflected in the number of rings representing the energy levels of the electrons. When we look at the diagram on the bottom, we see the force of attraction is indicated by the thickness of the arrow. You'll notice that with lithium, because there are so few electrons and so few energy levels used, that places the valence electrons rather close to the nucleus. In the case of potassium, that one valence electron is quite far away. There are now 3 layers of electrons, kind of like running blocker, and interrupting that force of attraction on the valence electron. So the more electrons within an atom, as you go down a group, you're adding an entire ring full of electrons, an entire energy level, which pushes that valence electron further out and weakens the force of attraction. Again, the further away it is, the weaker the force. This pattern will apply in all groups on the periodic table if I'm looking at elements within the same group. Now, the other characteristic I can compare is looking at the number of protons and relating that to the attractive force. So consider for a moment that I increase the size of the magnets and I keep them at a relatively similar distance. So when you look at A, if I have only, say, one proton and one electron pulling on each other, and then in F, I increase that to, say, 4 protons and then technically 4 electrons. Think of that like creating bigger magnets. The smaller the magnets, the weaker the force of attraction. So if I have 2 very large magnets modeled in situation F, the chance that they would attract to each other at a certain distance is much higher than if I would compare that to little magnets. So as the amount of charge increases, so does the force of attraction. Again, let's look at that in the context of some elements. Here I would be looking across a group. So starting with sodium and then moving to aluminum and chlorine, we see that I am adding protons to the nucleus. So sodium has an atomic number of 11. Aluminum has 13 protons in the nucleus and chlorine has 17. However, all of the electrons that are being added are all being added to the same energy level. So you can think of that as a similar relative distance. So now as I go to the right across the group, I'm increasing the amount of positive and negative things pulling on each other. So as you go across to the right, you're increasing the force of attraction as more protons and more electrons attract towards each other. As you do your POGL coming up, you will look at several different properties that show trends across a row and down a column. As you consider things like atomic radius and electronegativity and ionization energy, which are all presented in the model, you will be asked to explain that in the context of Coulombic attraction. So always think about the size of the magnets and the distance between the magnets as an explanation to back up the patterns that you are seeing.